Okay, so this is me. My name is Sumit. My area of expertise is data science, and I'm going to tell you a bit about the data science work package. In particular, what are the overarching aims? And what I would also like to do so that I don't stay too much at just a managerial level, hopefully I tell you a bit about the techniques we favor to achieve those aims. And so there's going to be a small amount of depth, but not too much. Okay, so essentially, data science, it's something that National Highways and Coastal are investing a lot of money in, and it's important for you guys to deliver on your priorities. And presumably, you do lots of it, and you want to do more of it. And in particular, what we hope to do in this work package, in addition to solving our problems, is also facilitate or also enable some of your aims and ambitions in this area. So what I wanted to illustrate with this sort of Venn diagram is where the Cambridge team's strengths really lie. So what is a data scientist? I mean, it's somebody that sits in the intersection of perhaps computer science, mathematics and statistics, and an application domain, which is the one at the bottom here. I would say the Cambridge team is our generalists. So we basically excel in the mathematics and statistics and underpin data science. So what I do and the other chief investigator, Professor Mark Girolami, we spend a lot of time developing algorithms of generic importance for data science. And I'll try to give you a few examples of this. They're not in the infrastructure domain just yet, but I'm going to hopefully convince you that they are relevant. And then we've got members of our team who do apply data science to transport infrastructure, inspection and maintenance. Okay, so now this is probably some of you even authored this, so I'm not going to hope to tell you what I think you wrote. But just to say that these highlighted bits in yellow, although the wording may be slightly different, in essence, what we're going to do is going to resonate with that and maybe even enable that a lot more. So let me just go through the team with you. So this is the team. On Digital Roads, we have Professor Mark Girolami. You perhaps met him before today. This is me here on Future Roads. And I've had the pleasure of dealing with Tim because we've been interviewing for the Costain Industrial Fellow, Alex, who will be starting in August. And I'm indebted to George Hadjidimitriou, who's helped me basically pull this presentation together. So we sat together and we worked through what we were going to say, but George really was the architect of everything you see here. And then we've got our Future Roads Fellow, Yiming, who is starting in September, and our PhD student, Zening. Okay. Now, I said that we're a bunch of generalists, okay? So what do I mean? So if we go from left to right here, we are essentially moving from methodology to applied work. And if we go, similar sort of transition on the bottom half of the picture, of this illustration. So we've got thumbnails or problems we've dealt with. I don't want to touch on everyone, but just I'll point a few out. Like, for instance, this one here was, we're interested in doing Bayesian computation on the cloud, okay? And if you don't load balance your computations properly, you end up with a lot of the processors idling while the rest are doing their thing before you can do the bits that's asynchronous. So this is sort of stuff we work on. I'm interested in automation and control, and it's going to feature in this work package. Alex, who is a specialist in time series data, so she's been working on enhancing these very dim images from live cell microscopy, okay? And she'll be joining us in August. And basically the skills are not disjoint, as you will see, okay? And then bottom here are basically some of the work that that our Future Roads Fellow will be doing, and George does, which is basically applying data science to transport infrastructure, maintenance, and inspection. Okay, so this is an overview of the packages. Okay, so there are 4 main tasks. You've probably heard a lot about uncertainty quantification. Okay, it's a phrase that's been bandied around quite a bit. And I hope to tell you a bit of what that means. So the first task is really this business of understanding what are the engineering insights we want to deliver, we want to understand, and then sourcing the data for it. Okay, so that's the first task in essence. And then basically the first task is a process of understanding what is it that we want, what insights we want to draw, sourcing the data, building the models. Okay, that's what's done in the first task. But you're not really interrogating the models, you're not computing with them just yet. Okay, and that's what the second task does. And then task 3, and so basically, if you've ever picked up a book, you may have heard of the word Bayesian. Essentially, this is the techniques we favor are Bayesian techniques, and these basically fall under the umbrella of Bayesian modeling and learning. And the last 2 tasks are really the automation ones. And again, we're going to adopt a Bayesian approach, and I'll tell you a bit more about them. So this task is more about automating low-level processes or menial processes. So for instance, not really the strategic ones to do with the deployment of assets to meet certain maintenance requirements. Okay, so I'll tell you a bit about this as we get through the presentation. Okay, so we're going to focus on the first 2 tasks. And I'm just going to give, essentially this is the only sort of variables you'll see, and then we won't see them again. Okay, so the techniques we favor are Bayesian modeling and learning. And what we've been doing, what the team has been doing, and I said we were generalists, so Professor Mark Girani and myself, we don't work together necessarily, but we converge on the sort of problems we're interested in. We've been working for many years now for delivering solutions for analyzing data that evolves over time. Okay? So data that evolves over time, you can, what could this data be? Well, Y1, Y2 could be images. It could be the price of a financial asset. I've never made any money from it though, but it could be that. It could be the position of vehicles or other assets you're tracking, okay? Though that's a navigation task. And the one that we're utterly bored of, it could be the incidence of an epidemic, right? Now, to explain this observed data, there's, this observed data can't be explained without the physical process that's generating them. And really, this is what we're trying to get at. So let's look at the usual example that we've all heard umpteen times, is this business about an epidemic. So we get data that records the number of infections, but what we're really after is the health of the population. Okay, and health of the population can be captured very simply as the number of susceptible individuals infected and recovered. Okay, and the data is only ever going to record, only going to give us a very censored, imprecise observation of the health of the population. And what we need to do is really, we need to build a model that describes the evolution of the physical process. So this is where, if I was interested, say, in modeling the deterioration of a material, I would go to Abir and say, you understand materials, how they deteriorate over time. Can you help me model that? And then once you've built the model, so this is really the first 2 tasks, then the first task rather, and then we are going to interrogate the model and get our insight. So really, if you go back to the epidemic example, it's very hard to process, to invert the data, rather to invert the data and get back to the underlying physical process you're really after, which is basically how many people in the population are susceptible, infected, or recovered. And this is where a lot of our work has gone into. We've been constructing algorithms that solve these sort of problems where data evolves over time, and there is a physical process generating it. And we've come up with generic techniques that are useful, and we hope to apply them to this initiative as well. Okay. How many minutes do I have? Don't know.
I thought Tim or.
Keep on going.
Okay. All right. Okay.
Right.
All right. Okay. So let's look at what data integration entails. So these are the work package. Basically, the activities of the work package. And let me just paraphrase it. Okay. There will be slight mismatch between what's written here and what I'm saying, but the idea is the same. Okay. So the overall objective here is to enhance our engineering insight using data. And we always assimilate data with our models in a Bayesian way. That's just my upbringing, and it happens to be the most effective way, in my opinion, anyway. So we need to identify the engineering insights we're interested in. So for instance, if you want to just locate defects in a pavement, then maybe just capturing images are fine. But if you want to understand the health of how the material degrades over time with weather and load, then really you have to instrument the pavement, right? You have to understand how it's cracking and fracturing over time. So really, it's about identifying the engineering insights with help of National Highways and Coastal, and then we go and source the data that potentially could reveal the insights. And then we have to build the physical models that relate the deterioration of the pavement to the recorded data. Okay, and that's essentially the task. This task here, which is the first task, is to create a set of problems, tasks, specific use cases, informed by NH and Costain, and a set of models that we hope to be able to interrogate next to reveal the insights we're after. Now, presumably, we're not going to be the first ones who have ever done this. So there are going to be competing techniques that you probably have in-house, and also ones that are published in the open literature, and that's something we need to benchmark against. Okay, so this is what we're going to do in the first task. Okay. Now, we have sourced data, we've sourced the data, we've constructed models. Now we need to interrogate the model and get the answer. Okay, and the answer is going to come with uncertainty, and I hope to just explain to you in a simple example what this business of uncertainty is all about. So here's a problem which you solved before at a PhD student of mine, and here we have GPS measurements of a vehicle, a taxi in this case, traveling in a dense urban environment that started off somewhere here and ended up somewhere here. Now these GPS measurements are recorded every interval of time, perhaps 15 seconds or more. And they're not exactly on the road network. You can't see it here, but for a more sparse data set that actually starts here and ends at the top, you can see, for instance, some of these measurements are just not on the road. Okay? So the question you want to ask yourself is identify the route the vehicle took from the start location to the end location that's most consistent with the data. Now, if we are absolutely confident that the vehicle only travels the shortest path, okay, the driver only ever takes the shortest path, then there's no uncertainty here. It is only one solution to this problem, which is the shortest path that takes you from the bottom left to the top right. But that's not how drivers work. They have an aversion to longer paths, but they will take them. And it is because of that there could be more than one route that explains the data. And what I've displayed here is not, the driver didn't actually move in loops. I've just overlaid the sort of paths that could account for the data. So by uncertainty quantification here, I mean I need to generate all possible solutions that are consistent with the data, okay? And I need to assign them some probability to say that, okay, I should rank them from high to low to say I think these are the highest ranking solutions and these are the lowest ranking ones, in a nutshell, okay? So that's what uncertainty quantification is all about. So what's our next task? So we spent a lot of time building the models, building the physical models, perhaps interacting with Abir. And now what we're going to say is that, look, we're going to admit and say there are sources of uncertainty here. Not every parameter of the model is fully known to us. We have to identify all the parameters of the model that are not known to us entirely and identify suitable ranges for them, okay? So that's basically revisiting the modeling phase and accounting for all sources of uncertainty. And even our data itself, it's noisy. It could be sparse, it could be out of sequence, and in fact, you don't even really know. If somebody says I measure a temperature in noise, you don't really know how much that noise is, and in fact, that's also something to be uncovered as part of the solution. So, for these reasons, when we interrogate the models with uncertainty taken in, we're going to end up with scenarios for what the physical process could be doing that best accounts for the data. Okay, now. These are the gold standard. So my favorite technique is Monte Carlo, Markov chain Monte Carlo. These are gold standard techniques in inverting data to get at the physical process. But depending on the problem size we are dealing with, it may be infeasible. Okay, so we need to also look at other techniques. There are very popular machine learning ones like variational approximation, Gaussian processes. So really at the end of this work package, what we need to be doing, what we should have done, is to deliver a set of algorithms for the benchmark, for the test case problems in the previous work package, for which we deliver solutions with uncertainty quantified. And these are not meant to be so case specific that you wouldn't be able to port them to other similar problems. Okay, I think I'm probably running out of time, so let me just say one thing about automation, a few things about automation rather. I don't want to, because I need to basically tell you how we're going to achieve this. Okay, now it occurred to me when I wrote these slides, and it's Yanis insisted that they be uploaded, that this I probably have to explain myself, because this is probably very odd to most of you. Does anybody know what this is? And please, those from Cambridge, from the engineering department, don't put your hands up, okay? Does anybody know what this is? Yep.
Is it the rescue robot?
Okay, yes, very close. It's actually it's actually a benchmark problem in robotics that people often use in machine learning that lives in a repository called AI Gym. This is actually a two-dimensional robotic animal. And the aim here is actually to get the animal to walk. And it's not easy because all the joints are actuated. And even to get the animal to stand, you have to basically you have to actuate the joints the right amount, otherwise it won't stand. And once it stands, you've got to get it to walk, okay? And so that's the task, and this is a benchmark problem that is very difficult to solve. So my approach to automation, which I think will be relevant for this project, is a Bayesian approach, which is essentially automation by mimicry. So we've got experts who are very good at, say, playing games, who are very good at driving cranes, who are very good at piloting drones. So we're going to get the expert to demonstrate the tasks to us and generate a whole lot of data, the state of the system, the action the expert took, the next state, the action the expert took, and so on and so forth. That is going to be captured. And then what we're going to do is we're going to fit a model to best describe what the action expert did and then to use that fitted model to extrapolate to automate in a novel setting. And the technique we favor is neural networks. You've probably heard it many times. And this is our approach to automation. And essentially, it's something that's widely used, maybe not the Bayesian neural network approach, but at least this approach to automation is widely used. A master's student of mine applied this to model clinicians' behavior when they deal with sepsis in patients. And also, remote expert crane operators and so on, people who fly drones. You can basically, there's ample sources of such data. You could capture the data, try to explain the expert through a neural network and say, look, when I'm faced with a novel setting, I could automate it in this way, okay? So now what we would like to do in these two packages is use that technology and proceed with automation. So just to paraphrase, we know the automation guy is going to come up with robotic methods and concepts for maintenance and repair, okay? Now these will either be manually operated or semi-autonomously operated. There'll be a lot of data generated from them, and we hope to take this data and apply that technology before and fully automate the process. Okay, so this is sort of low-level automation. Okay, it's automating sort of menial tasks to do with inspection and maintenance. And I don't mean that word in a derogatory way. I just mean it in a sort of like, it's not really a strategic automation task. Okay. Now, the next work package is going to try to do things more strategically. It's going to pull all these things, all these elements together. And essentially, I want to focus on just basically this aspect here. So if we are going to deploy assets for inspection and maintenance, so what we need to do is we can't just be reactive and say, there are problems here to be addressed, let's deploy the assets. We actually have to look ahead and see what might crop up in the future, because these assets that are engaged in the current task will not be available in the future. So that problem is also an instance of a control problem. It's the deciding on the best strategy to deploy assets. You really need to look ahead through simulations of the future and decide where those assets might be called for in the near future in making that decision. So really, this is a strategic control problem, rather dealing with decision making at a higher level. So that's the sort of final task we hope to be able to pull all those elements together in dealing with. Okay, so this is the Gantt chart. We're in month 3, I think. So recruitment is almost there now. Okay, so I won't go through the details. Let me just summarize. I'm probably over time. So what I've done today is I've overviewed the work packages and our methodology we favor in solving them. Okay. The work packages were all about sourcing data and creating models, interrogating the models once you have the data, and uncovering the true states of the physical processes you're after, using the same idea to automate low-level robotic, low-level maintenance and inspection tasks, and then pulling them together to automate more strategic tasks. Okay. Now, the success of this hinges on really, a collaborative approach, with NH and Costain in defining the sort of the test cases, the data, the models, quantifying the quality of the data, is the data fit for purpose, and so on and so forth. Now, there's an element of this work package which is sort of formulaic in the sense that there is best practice out there. We just have to funnel it for our objectives. So there's a bit of what we're going to be doing is essentially identifying best practice, developing and refining it in the context of this initiative. And then there's an element which is also ambitious, and this is something Abir Weirdwine kindly provided me with today. Essentially, the ultimate goal is really to deliver a smart digital tool that is going to pull all these 4 packages together, and it's really going to hinge on data science. So a lot is resting on how we perform in this package, and looking ahead, it's not so clear how those tasks, how it's all going to be pulled together, but we hope to, we think we have a decent idea on how to start. Okay, so that's does anyone have any questions? Yep.
Did have one? Okay. I did not understand.
Oh.
I love that. I can't use Bayesian in a sentence.
Okay, fair enough. No, it's okay.
Thank you. So, although I can't use Bayesian in a sentence, I do understand a little bit about managing uncertainty.
Okay.
And some of the other bits you were talking about, automation.
Yep.
What my question is how would you consider prioritizing some of those things? So there's some uncertainties that we're actually really good at managing that maybe don't have a particularly big impact on our decision making.
Yeah.
And there are some tasks that we're relatively happy to leave in the hands of experts, especially as we often need the accountability that goes with that.
Yeah.
So how are you proposing to prioritize the difference between the things that might be easier to automate or easier to model versus the things that might deliver the most value for the industry?
Well, the academic solution answer to that question is that we always take the low-hanging fruit first, because in a way it informs what we do next. So I don't really have a better answer than saying that it's a process of discovery for us as well, because it's a new collaboration, a new applied domain for the data science team. So it's something. Okay, so at the moment I can't provide the concrete answer, but hopefully in the near future.
Maybe to follow up on that, what are your initial target processes that you think you may want to roll out as?
We have a framework. We have a framework for doing it. We have a framework for doing it. We don't have the target problem cases yet. So it's something that we very much hope that you would tell us what's a priority for you. And a lot of the methods we've developed really is the go-to place to test them is really this sort of AIG, which is this benchmark that people apply machine learning techniques to sort of compete against each other. Yeah.
Thank you, Sumit. Deepika from Costain. So one of the challenges, what I understand from my customers, both in transportation and energy, is the data quality.
Okay.
I know you have touched upon the uncertainty, and the challenge they have that the data sometimes is that poor, and especially when we are going to touch about legacy in the slides I saw, that in order to convert them into useful insights and some kind of forecast, they are so poor that they have to invest a lot of time, resource, and money. Still they can't get.
Okay.
So I understand that you have talked about uncertainty qualification, but have you thought about a kind of a bandwidth or a tolerance within which it will still make some sense? Because so much of money and investment, everything falls on these kind of forecasts which we create from them. So is something like that built in?
So we know how to assess the quality of data. I mean, we have got some tools to assess. So basically, you need to understand whether the data is good enough for the underlying task. And there are some generic measures of quality. So I would, if I were trying to convince a customer that that perhaps they need to invest in the data to get a better quality answer, perhaps what I would do is to come up with a sort of a simulation, a rudimentary simulation, to show what their data can produce. Because we could simulate the processes involved, we know what the ground truth is, we can say, look, this is the best I could do with your data. If you were to change its parameters slightly, we would get much better answers. So, in essence, the answer to your question, as well as I understood it, would be we have tools to assess the quality of data, and we think we can reasonably convince people what's doable and not. But we can't work magic, no. Okay? All right, should we stop it? Okay, thank you so much for your time.